In this tutorial, we are going to talk about the interference of sound wave. So what is the interference of sound wave? So when two or more sound wave from different sources are present at the same time, they interact with each other to produce a new wave. Now, when you have two waves, when those two waves interact with each other, they are going to produce a new wave. So there are going to be an interference which is going to happen between those two waves. Okay? So under interference of sound wave, one thing you have to understand is that we have two types of interference. We have what we call the destructive interference, destructive interference, interference, and constructive interference. Constructive interference. Now, in some books, you discover to say destructive interference is the same as relative minimum. Relative minimum. So if we're talking about relative minimum, if you come across any question they're asking about relative minimum, then you are talking about destructive interference. Relative minimum. Then this is what we call relative maximum. Relative maximum. So if you come across any question asking about relative minimum, then you are talking about destructive interference. If you come across any question asking about relative maximum, we are talking about constructive interference. Now we are saying that if we have got two waves, if those two waves they are going to interact, they are going to interfere each other. So it can either form a destructive interference or constructive interference. So let's begin our discussion with destructive interference. So what is destructive interference? So if you have two waves, if this is my first wave which I have, okay, it's going in that direction. Let's say the amplitude is 4, okay. Then we also have another wave plus another wave is here. Let's say the amplitude now, instead of it going in that direction, it will go to the positive direction. Let's say we have -2. So the results, if we add these two waves, the amplitude is going to be 4 minus 2, 4 plus -2, which is going to be 2. So the results which we are going to have will be 2. So destructive interference has happened. So this wave is going to be distracted by the first wave. So that's the basic idea behind destructive interference. So it is very, very important for us to understand this. Now, the basic example which you can understand destructive interference is this. Let's say we have sometimes, like I've said, this is what we call, sometimes they'll call it relative minimum or they'll call it intensity minimum. Okay, so sometimes let's say we have a person, let's say this is Mark, this is McDonald, and then let's have two people. I'm going to have Lombe here, then I'm going to have another guy. Let's have Natasha. So if this is Natasha, so this is the person, the distance is the same, okay, the distance from there and also the distance from here. So what we have to understand is that there is a music coming from Lombe and there's also music coming from Natasha. Okay, then Mark has to listen to both songs, okay, which is being played by Lombe and Natasha. So let's say Lombe is playing a song done by Yomaps Kondwa. Then Natasha is playing a song done by Chirewan Nayo Nayo. Okay. So what is happening here is that, let's say the volume, maybe these two guys, Lombe and Natasha, they are using phones, okay, or they are using maybe a speaker or something. Now the volume, let's say that the volume for Lombe, the one for Kondwa, for your maps, is on the volume she has increased the volume all the way to 20. Okay, then Natasha has increased the volume all the way to 15. Now, the distance is the same. The distance from Lombe to where Mark is and the distance from Natasha to where Mark is the same. Let's say the distance here is 6 meters, even here is 6 meters. Okay. Now, one thing we have to understand is that since the volume for Lombe is bit greater than the volume for what? Natasha, then the song done by Chirewan Nayo now is going to be distracted. Mark will not hear anything for Natasha in this case because Natasha's volume is at 15 and Lombe's volume is at 20. But again, it's not that if the frequency in this case at the volume of 20, if the volume is at 20, it doesn't mean that Mark here is going to hear the frequency which is at 20. Okay, some of the frequency is going to be distracted by Natasha. Okay, so now what you're going to do is going to be 20 minus 15. So 20 minus 15 is going to be 5. So that is what you are going to discover. So that is destructive interference. So some of the frequency for Natasha is going to be distracted by Lombe. Okay, so that is what we call destructive interference. So destructive interference is very, very interesting. You need to know and you need to understand this. So like I've said, destructive interference, it is also known as relative minimum or intensity minimum. That is destructive interference. Okay, now that we have talked about destructive interference, let's go ahead and talk about constructive interference. So what is constructive interference? So constructive interference. So we need to have also two waves. So constructive interference, we said, is also known as relative maximum or intensity maximum. If I've got two waves, if these two waves are going to interact, now these ones, they are going to be moving in the same direction. Okay, so if this is 2, the amplitude is 2, there the amplitude is 3. If I add these two, a constructive interference is going to occur, meaning that it's going to be 2 plus 3, the amplitude will be now 5. The wave will be generated in that manner. That is what we call constructive interference. Okay, so now what if I have got the same example which I gave you under destructive interference? Let's say we have two people. Now I'm going to change. This is Betha. Then I have also another person here. Let's say this is Erica. Then this is Annie. So let's say I'll use the same thing. The distance will be the same. Okay, then the volume for this one, let's put that the volume will be maybe at 20. The volume for this one will, let's just put it 10. Now constructive interference will have the same things. So Elika is playing a song done by Yomaps, which is Kondwa. Then also Annie is playing a song done by Yomaps, the same song, which is Kondwa. So it is the same song. Now the volume here, it is at 20. This the volume is at 10. So these, they are going to construct as the voice is approaching Betha. Okay, as the sound is approaching Betha, these two sounds, they are going to emerge, they are going to construct. So instead of just hearing the frequency of the volume of 20, it's going to construct. You are going to add this and that. So you discover to say Betha is going to hear a loud sound than the way it was here, because these two, they are supposed to add up. That is a constructive interference. So they will construct. So that's the basic idea behind these two things. So that is what you need to know under destructive interference and constructive interference. Now let me give you an example. So the general principle which you need to understand is that for a destructive interference to occur, if you want a destructive interference to occur, for a destructive interference to occur, the original length must differ by plus or minus half the wavelength. Then for a constructive interference to occur, the original length must differ by plus or minus just a wavelength. This is something which is very, very important. So the only things which you need to know here is that for a constructive interference to occur, the original length must differ by a wavelength. Then for a destructive interference to occur, the original length must differ by plus or minus the wavelength. Now, why are we saying plus or minus? Let's say that we have got the lambda. Let me just give you an example here. The best example I can give you is, let's say we have two speakers. Okay, let's have speaker A and speaker B. Okay, and let's say the person is here, so the frequency will be the same. That is the person. Now let's say we are saying that the distance here and here is supposed to be the same. Okay, the distance has to be the same. Now if this is 6 meters, this is the person here. So now the question is, what must be L? Let me put L here. What must be L for a destructive interference to occur? What must be L for a destructive interference to occur? Let's assume you always be given the frequency. Let's say the frequency in this case is 40 hertz, or let me put 80 hertz. If the frequency is 80 hertz, and if they are not mentioning anything about the velocity at all, the velocity you use the speed of sound in air to be 343 meters per second. You use this, we are considering the temperature to be at 20 degrees Celsius. But if they are going to mention about the temperature, then you have to use this formula to find the velocity. The temperature in Kelvin divided by 273. So if you have been given the temperature in degrees, you have to convert that. You say the degrees plus 273. Then you plug in. Now if they are not mentioning anything about the temperature and anything about the velocity, we always use 343 meters per second. Take note of that. If they're not mentioning anything about the velocity or anything about the temperature, use the speed of sound as 343 meters per second. Okay. Now the question is, from the diagram which we have here, what must be L so that destructive interference can occur? Okay. So for a destructive interference to occur, so I'll say what must be L for a destructive interference to occur. For a destructive interference to occur, this L must be the original L, because this L and that L is the same, like we said. So it's going to be 6 plus or minus half a wavelength. That's the formula I've given you. So for a destructive interference to occur, the original length, which is 6, must differ by half a wavelength. Now first you need to find the wavelength. How do you find the wavelength? V is equal to the frequency times the lambda. Let's divide both sides by the frequency. So lambda will be equal to V divided by frequency. So this will be equal to 343 divided by 80. So lambda will be equal to 343 divided by 80. That should be 4.29. So 4.29 meters is my lambda. Now that I have my lambda, what must be L for a destructive interference to occur? So L will be equal to 6 plus or minus, then I have half, then 429, like that. meaning that 6, I'll say L has to be 6 plus or minus, I'll say 4.29 times 1 over 2 is 0.5. That is 2.15. Now, the L, it can be two things. For destructive interference to occur, L can be 6 plus 2.15, or L can be 6 minus 2.15. So you say it can either be 6 minus, or I'll start with plus, 6 plus 2.15. So L must be 8.15 meters for a destructive interference to occur, or L must be 6 minus 2.15, or L must be 3.85 for a destructive interference to occur. So for a destructive interference to occur, L must be 8.15 or 3.85. But there are some times where you can just represent this, you can present this in just one answer. You just remove negative, just go ahead with the positive. That is just okay. No one is going to penalize you. Okay? You can just go ahead with just positive. Okay? Now, I'm going to show you, now what about constructive interference? What must be L for a constructive interference to occur? What must be L for a constructive interference to occur? Remember, our lambda was 343 divided by 80. Our lambda was 4.29 meters. So for a constructive interference to occur, the original length must differ by plus or minus a wavelength, meaning L will be equal to 6 plus or minus lambda 4.29. So for a constructive interference to occur, L should be 6 plus 4.29, or L should be 6 minus 4.29. Okay? Meaning my answer will be, for a constructive interference to occur, L must be 6 plus 4.29. For a constructive interference to occur, L must be 10.9, or L should be 6 minus 4.29, or L should be 1.71 meters. So if I have got this constructive interference will occur. But like I've said, it's possible you can just go ahead with just positive. That is just okay. Now, since I've given you the basic idea behind constructive interference and destructive interference, let's go ahead and see how we can work around with different questions. So the first question is, a acoustical system shown in the figure below is driven by a speaker emitting a sound of frequency 756 Hz. If constructive interference occurs at a particular instant, by what minimum amount should the path length in the upper U tube be increased so that the destructive interference occur? Okay. Then the second question is saying what minimum increase. Now in this case we are just interested in increase. Here there is increase, even here there is increase. I'll only work around with positive. If they use decrease, you use minus. What do I mean? We are saying that for destructive interference to occur, the original length must differ by plus or minus half a wavelength. For a constructive interference to occur, the original length must differ by plus or minus a wavelength. So if they use increased, in this case they have specified, you only work around with the positive. If they use decrease, you work around with the negative. Okay, so in this case we just go ahead with the positive. So now in this case, since they are just saying what minimum amount should be the path length in the upper U tube be increased so that the destructive interference should occur. So I'll say I need first to find, I've not been given any information about the velocity. Remember I said if I've not been given any information about the velocity, you use, so this is my frequency, you use V to be 343 meters. So you always find first the wavelength. That is must. So now V is equal to F lambda. So lambda will be equal to V divided by frequency. So lambda will be equal to 343 divided by the frequency 756. So lambda will be equal to 343 divided by 756. So I'm going to get 0.45. Okay, I'm going to get 0.454 meters. That is my lambda. Now, for a destructive interference to occur, remember, the original length in this case, we have not been given any length. In fact, we're not even interested in the original length. So we'll say, for a destructive interference, we're starting with a destructive interference to occur. The original length must, so it's going to be plus half a wavelength. So now, for a destructive interference to occur, it's going to be the length, then half, the wavelength is 0.454. So destructive interference to occur, meaning I'll say 0.5 is 1 over 2 times 0.453 or 454. So meaning 0.227. Meaning that for a destructive, so you say this, since I don't have L, that's why the question is specifying here to say what minimum amount should be the path length be increased, meaning this should be increased with how much. So it has to be increased by 0.227 meters. So you say it has to be, for a destructive interference to occur, the length must be increased by 0. So you say for a destructive interference to occur, the original length must be increased by this 0.227 meters. Then for constructive interference, now you do the same, but for constructive interference, you know that for a constructive interference to occur, the original length must be increased by the lambda. So I'll just say this plus lambda. So it has to be increased. For a constructive interference to occur, the original length must be increased by 0.45 meters. So that is it for this question. Now I also have this interesting question here, which is a pair of speakers separated by a distance of 0.7 meters are driven by the same oscillator at a frequency of 686 Hz. So you always be given the frequency. An observer originally positioned at one of the speaker begins to walk along the line perpendicular to the line joining the speaker as shown in the figure. Part A. How far must be the observer walk before reaching the relative maximum in intensity? I explained this. Once they are talking about the relative maximum, what are we talking about? The relative maximum, we are talking about the constructive interference. But B, how far will the observer be from the speaker when the first relative minimum is detected in the intensity? Okay, relative minimum, we are talking about what? Destructive interference. So let's start with constructive interference. So what is standing wave? So standing wave is just basically a vibration of the system in which some particular point remain fixed while others between them vibrate with the maximum amplitude. What do I mean? What I mean here is that the amplitude and the frequency remains the same. Okay, in this case. So what is happening is that it is called standing wave because the length doesn't change, so it is just fixed. You can see that I've got two pillars here from this diagram. I've got this pillar and that pillar. Now in between I've got a loop. Now the length of this loop is not going to change. No matter how much I can produce waves, the length will be the same. So the length doesn't change. That's the reason why we are calling it a standing wave. Okay, the length will just be fixed. Okay, now if a force is applied in between here, a wave is going to be generated. What do I mean? So if a wave is going to be generated, it can be generated in that manner, or okay. Now what if I have got two pillars and then a wave has been generated? Let me just draw this. I have this, I have applied a force now here. You plug it, then a wave is going to be generated. That is a wave. Okay, a wave has been generated. So you discover that this length will remain the same, will not change. I can also have another one, a different wave can be generated as well. Okay, so another wave like this, it can be generated. I can also have a different one. Okay, then let's have this. So a wave like this will be generated. So we can clearly see that we can have many number of loops. Okay, now if you have got a wave which is in this form, if you have a wave in this form, this part here is what we call the node. This is the node. This part here is what we call the antinode. The antinode, if you hear antinodes, it's the same as the number of loops. Now you discover to say the nodes here, I've got three nodes, then I've got two antinodes. So here I've got one, two. I've got two nodes, but I've got only one node, antinode. Then here I've got one, two, three antinodes, or three nodes, and then I've got one, two antinodes. Okay. Now the trend which I want you to see now here is this. I'm going to have the first one, which is here. This is a node, a node. Then another one, which is like that. Then another one will be like that. Then let's have the fourth one, which will be like that. Okay. So this is a node, a node, node, node. This is antinode. This is antinode, antinode, node, node, node. Again, this is the antinode, antinode, antinode. Then you have got node, 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 node. So you discover to say the first part here, we have got two nodes and one antinode. The second part here, we have got three nodes and two antinodes. The third part here, we have got four nodes and three antinodes. Then this one, we have got 1, 2, 3, 4, 5. We have got 5 nodes and 4 antinodes, which is 1, 2, 3, 4. 4 antinodes. So we can clearly say that we can come up with a formula to say from the first part here, if I've got two nodes, so a node, meaning that for us to find antinode, antinode is just is going to be equal to a node minus 1. So the first part, if I have got two nodes, for me to find the antinode, if I do 2 minus 1 is going to give me 1. At the same time, I can say node is equal to the antinode plus 1, which is just the same thing. So in this case, if I've got one antinode plus 1 is going to give me 2, which is 2 nodes. So this is a formula which you need to be familiar with under nodes and antinodes. But like we have said, n is the number of loops. So number of loops is the same as the antinode. These are number of loops. These are loops. This is a loop, a loop, a loop, a loop, a loop, a loop. Okay. So now when we're talking about the antinode and node, what you should be remembering is when we're talking about the antinode, it's the same as the number of loops. Okay. So if you know the number of loops, meaning you know the antinode. If you know the antinode, you can say antinode is equal to node minus 1. Okay, or node is equal to antinode plus 1 to find the antinode. If you know the to find the node, if you know the antinode. Okay. Now let's go back to our diagrams here. The first one here is what we call if n is equal to 1. If I've got only one loop, then we are dealing with the first harmonic. The first harmonic, this harmonic, it is the same as the overtone. It is also called overtone. At the same time, it is called the fundamental frequency. So if we're talking about the first harmonic, first overtone, and first fundamental frequency, we are still talking about the same thing. The second harmonic, the second overtone, the second fundamental frequency, we are still talking about the same thing. Okay, so if n is equal to 1, we are dealing with the first fundamental frequency. If n is equal to 2, the second fundamental frequency. If n is equal to 3, just like that. So n can be anything. N can be 1, can be 2, can be 3, can be 4, and so on and so forth. Now, one thing we need to understand here, if we talk about the wavelength, since we know that length, the SI unit is in meters. Also the lambda, the SI unit is also in meters. Now, let's rewrite the length in terms of the wavelength. So the first part which I have here, we can clearly see that if I've got a wave which is like this, that is one wavelength. Okay, because I've got this is half and that is also half. Half plus half is going to give me 1, meaning that the first part which I have here, it is just half a wavelength, meaning that L can be written as 1 over 2 a wavelength. Okay, what of here? This is the wavelength, which is the same as 2 over 2. So L will be equal to 2 over 2 the wavelength. Then here I'll have it's more like I've got half, the first part, which is half, half, also half. So from here to there is half, there half, also there half. So half, half, half is going to be 3 over. So L will be equal to 3 over 2 lambda. Now you can clearly see that if I have got 4, it's going to be L is equal to 4 over 2 lambda. So you can clearly see that the denominator will not change. We'll still have 2. Then we can say that this L is given by n divided by 2 times lambda n. Lambda n means we don't know the lambda we're talking about. That's why I'm putting it as lambda n. Okay. Now in this case, what we need to understand now is that since we have come up with this formula. N is the number of loops. In the first part, we have got only one loop, so n is equal to 1. That's why we have got 1. The second part, the number of loops, we have got 2. That's why we have got 2. The third part, the number of loops is 3. That's why we have got 3 on top. Okay, so n is the number of loops. Now this formula is very important. Okay, if I know the length, if I know the length, I also know the number of loops. I can use this formula to find the lambda. So this is the same as L is equal to n lambda n divided by 2. Let's cross multiply. We make lambda as a subject of formula. N lambda n will be equal to 2L. Divide both sides by n, both sides by n. So what I want you to understand is that this formula is very important, understanding waves. At the same time, since these will cancel, I'll also have another formula for lambda to be equal to 2L divided by n. This is also very important. Okay, now let's talk more about the fundamental frequency. Okay, so let me just get rid of this. Let me just get rid of this part here, and I'm going to put these formulas here. L is equal to n over 2 lambda n, and also another formula is lambda n should be equal to 2l divided by n. Okay, so this is what I'm going to do. So we want to find the frequency. So the speed of sound in air, if they will not mention anything about the temperature, just know that the speed of sound in air is 343 meters per second. Okay, now another thing which you have to know is that we want to find the fundamental frequency, since we have come up with the formula for the lambda. So V is equal to the frequency. Now the fundamental frequency, we don't know whether we are talking about the first overtone, the second overtone, so I'm going just to put Fn. So n is the number of loops, because if n is equal to 1, meaning I'm talking about the first fundamental frequency. If n is equal to 2, I'm talking about the second fundamental frequency. If n is equal to 3, I'm talking about the third harmonic motion. So I also say lambda n. We want to make frequency as a subject of formula. Let's divide both sides by lambda n. So the frequency n will be equal to V divided by this. Okay, so now we know that the lambda can be written by 2l divided by n. So let's replace now lambda with 2l divided by n, but this is the same as V divided by 2l divided by n. So V times n divided by 2l, meaning that the fundamental frequency now will be equal to n times V is nv divided by 2l. This formula is very important. If I know the velocity, okay, now you only use 343 if they have not mentioned anything about the velocity. If they give you the temperature, you need to find the velocity using this formula. 331, the square root of the temperature divided by 273 Kelvin. Now the temperature, if you have been given in degrees, you have to convert it to Kelvin. How do you convert from degrees to Kelvin? Add what you have. If you have maybe 10 degrees Celsius, add this 10 to 273, meaning that is now your temperature in Kelvin. Then find the velocity. Okay, now let's talk more about these formulas. So we have come up with a general formula for the fundamental frequency. Okay, so if n is equal to 1, meaning I'm talking about the first fundamental frequency, like I've said earlier. Now sometimes they can give you the velocity. We know also that the speed, the velocity of the wave on a string can also be given by the square root of the tension force divided by the mu value. Okay, you can also use this to find the velocity if you have been given the mu value. Now mu is the linear density. Linear density is given that by the mass divided by the length. So you'll be given the mass, the length, then you plug in the values to find the velocity. If you have been given the mass, the length, and the tension force, you can find the velocity in that way. Meaning that I can also say that Fn, which is the fundamental frequency, n divided by 2l times v. So I can replace v with this. Okay, therefore there is also this formula which you need to be familiar with: n divided by 2l times the square root of the tension force divided by the mu value. This formula is also very important. So n can be anything. N can be 1, n can be 2, 3. Okay, now another formula which you have to know for the fundamental frequency is this. Let's say we want to find the first fundamental frequency. Now I'll use this one. The first fundamental frequency is going to be f1. If n is equal to 1, n times v, 1 times v is going to be v over 2l. That is the first fundamental frequency. What if we want to find the second fundamental frequency, meaning n is equal to 2? So it's going to be 2. Here let me just put 1. Okay, I want to show you something. It's going to be 2 times v divided by 2l. If n is equal to 3, we're talking about the third harmonic. it will be 3v divided by 2l. Now one thing I want you to understand here is that if n is equal to 4, it will be 4v divided by 2l. This part doesn't change. The only thing which changes is the n. Okay, this part here doesn't change. This part is the same. Therefore, I can say that Fn is equal to n times, if this part here is C, this part here, the one which I've just highlighted in white, is the first fundamental frequency, times the first fundamental frequency. So if I know the first fundamental frequency, I can also use this formula. If n is equal to 2, then I'll say 2 times the first fundamental frequency. That will be now the second fundamental frequency from these formulas. Okay, so this is what you need to know under fundamental frequency. That is very, very important. Okay, so now if n is equal to 1, okay, if n is equal to 1, then you discover that you just have this v over 2l. So this is the basic idea behind standing wave. Now let's see how we can try to solve some different questions under fundamental frequency. So the first question I have is this, which is find the frequencies of the fundamental, second, and the third of the steel wire 1 meter long with a mass per unit length of 2.00 times 10 to the power negative 3 kg per meter, and under a tension of 80 Newton. Part B, find the wavelength of the sound wave created by the vibrating wire for all 3 nodes. So in this case, okay, assume that the speed of the sound in air is, we have been given the speed of sound, which is just cool for the second part. Then suppose the wire is a carbon with a density of 7.8 times 10 to the power 3 kg per cubic meter, a cross-section area of 2.56 times 10 to the power negative 7 square meter, and an elastic limit of 2.8 times 10 to the power 8 pascals. Find the fundamental frequency if the wire is tightened to elastic limit. Neglect the stretching of the wire. Let's start with the first part. Let's first come up with data for part A. So part A, we know that we have been given the length. What is our length? 1 meter. What else? The mass. The mass is 2.00 times 10 to the power negative 3. Okay. Then what is the frequency? Have we been given the frequency? No. The force, which is the tension force, Ft, is equal to 80 Newton. Okay. So I'm going to solve this question using 2 different methods, because I think I've explained 3 formulas on how to find the fundamental frequency. So the question is, we need to find the second fundamental frequency. The question is, find the frequencies of the fundamental, second, and the third. Okay, second and the third. We are not interested in the first fundamental frequency. So for the second part, for the second fundamental frequency, n is equal to 2. For the third, n is equal to 3. Okay. Now, so if n is equal to 1, meaning we're talking about the first fundamental frequency. If n is equal to 1, that is what we said. If n is equal to 2, we're talking about the second fundamental frequency. If n is equal to 3, we're talking about the third fundamental frequency. So in this case, since we're talking about the third, we're reaching all the way to third fundamental frequency, meaning, okay, I'll explain what I want to explain on part B. Now we want to find, remember, we have this information here. So the fundamental frequency is given by NV divided by 2L. Okay. Now V, since we have been given the mass and the length, then V can be given by the square root of the tension force divided by the mu. So I can say Fn will be equal to n divided by 2L times the square root of Ft divided by mu. If you want, you can first find the velocity and plug in dialect here. So let's use this formula now to find the first fundamental frequency, or the second, since we're interested in the second and the third one. So the second, so n is equal to 2, the length is 1, so the tension force is 80. Then mu, how can we find the mu value? Like I said, the mu value is given by the mass divided by the length. So the mass is 2.00 times 10 to the power negative 3 divided by 1. So we end up having the same 2.00 times 10 to the power negative 3. So I'll have 2.00 times 10 to the power negative 3. Okay, so the second fundamental frequency will be, I'll have 80 divided by 2.00 times 10 to the power negative 3. Then I get the square root is 4,000. The square root of 4,000 is 200. So 200 times 2 divided by 2 is 1. So it's times 1, which is just 200. So it is 200 hertz. That is the second fundamental frequency. Okay, 200 hertz. What of the third fundamental frequency? So the third fundamental frequency, let me just put this fundamental frequency here, 200 hertz. Using the same one, meaning the third one, n will be equal to 3. So it will be f3 will be equal to 3 divided by 2 times 1. The square root of the tension force is 80. Then this is 2.00 times 10 to the power negative 3. So since we said inside there we found a 200, so we just say 3 divided by 2, then times 200. That is 300. So the third fundamental frequency is 300 hertz. As simple as that. Okay, so that is it for the first part. Now I can also use another formula. Like I said, I gave you two formulas. I mentioned to say you can also use this formula to find the fundamental frequency. Fn is given by n times f1, meaning for this one you need first to find the first fundamental frequency. So how can we find the first fundamental frequency? To find the first fundamental frequency, meaning I'm going to say, since we said Fn is given by nv divided by 2l, so the velocity, so it's going to be n is equal to the velocity, this is 1, 2, l is 1. The velocity is the square root of the tension force, which is 80, divided by 2.00 times 10 to the power negative 3, which is the linear density. So F1 will be equal to 80. Inside there it was 200. 200 times 0.5. 1 over 2 is 0.5, so it's 100. After finding the first fundamental frequency, now I can come here and plug in. I want to find the second fundamental frequency where n is equal to 2. So it will be 2 times 100. So the second fundamental frequency, using another formula, I'll still get 200 hertz. Even here I found 200 hertz. To find the second one is going to be 3 times 100, which is 300. And we also found what? 300 hertz. As simple as that. Okay. So that is very, very important for you to know how to come up with what? The fundamental frequency. Let's now jump to B. So part B now we have changed. Okay. We have changed, but the question is connected. Find the wavelength of sound wave created by the vibrating wire of all 3 nodes. So if I've got 3 nodes, 1, 2, 3. If I have 3 nodes, I expect to have 2 antinodes. Oh yes, 2 antinodes. Now we want to find the velocity we have been given already. Now in this case, this question is not even hard. The first fundamental frequency we said is 100 from the first question, from part A. The second one was 200. The third one was 300, and we've been told that the speed of sound is we need to use 343 meters per second. So we want to find the wavelength. So v, the first one, v will be equal to fn times lambda n. I want to find lambda n. So lambda n will be equal to v divided by frequency n. So if I want to find the first one where n is equal to 1, I'll use the first fundamental frequency. Okay, so I'll say lambda 1 will be equal to 343 divided by 100. So lambda 1 will be equal to 343 divided by 100. It is 3.45 meters. Then when lambda is 2, I'll say 343 divided by the lambda, that is going to be 200. Lambda 2 will be equal to 343 divided by 200. That is 1.72 meters. Then again, lambda 3 will be equal to 343. I'll use now 300. So it will be 343 divided by 300. That is lambda 3 will be equal to 1.14 meters. So this is the wavelength. The first one is that, the second one, and the third one. And this is making sense. If the frequency is less, we expect the wavelength to increase, because the frequency and the wavelength, they are inverse proportion to each other. So let's talk about standing waves in air column. So this is a bit similar to standing waves, the normal standing wave we have been doing so far, but only that in this case you are going to have a wave in air column. Let's say you have a pipe. Okay, if this happen to be the pipe, so if a wave is going to be generated here, so now here we are going to have two cases. So have the first part, which we are going to talk about, is the pipe opened at both ends. At both ends. Let me just put it here. So the pipe is open at both ends. Pipe open at both ends. So, and then a wave is going to be generated like that. Okay, so again the length will not change. The length of the pipe will be the same. It's the same as standing wave. The length doesn't change. So now we know that this is the antinode and this is the node. Okay, so now what we need to understand is that if I add this part here and that part together, they will make a half wavelength like that. Okay, so in this case, if the pipe is open at both ends, meaning this part only is half a wavelength, is 1/4, is quarter, is 1/4 a wavelength, even that one is 1/4 a wavelength, meaning that this length is the addition. We need to add 1/4 plus 1/4, which is going to be L. In this case will be half. If I add 1/4 plus 1/4, the denominators are the same, we add the numerator 2/4, which is 1/2. So have half a wavelength. So now this is totally different from the normal standing wave which we've been doing so far, because in this case we have got one node, okay, and then we have got two antinodes. Node is 1, then we have got antinode, which is 2. So now if I have another one, let's say we have two of these. like that. It is open, meaning that we know that this is 1 over 2, this is 1 over 4, this is 1 over 4. So again, this and that is going to give me half. So half plus half is 1. So you discover that this is going to be 2 over, it's the same as just 2 over 2. Okay, or it's the same as it's going to be L is equal to lambda, like that. So now one thing we need to understand now is that we are going to have if I have got 4 nodes, if I have got 1, 2, 3, then I've got, okay, let's start with the 3 one. So it is open at both ends. You are going to see that what we are going to have is going to be, this part is 1 over 4, this is half, this is half, and this is 1 over 4. So 1 over 4 plus 1 over 4 is going to give me half. Half, this is it's the same as I've got half plus half, again half, because 1 over 4 plus 1 over 4 is half. I'll end up having 3 over 2. So you discover to say the only difference with the normal standing wave is the node and the antinode, but we'll still have the same. So we'll still have n to be equal to 1, 2, 3, 4, 5. They'll keep on going. So now in this case, what we need to understand is that if the pipe is open at both ends, we'll still have the same. We'll have node is equal to 1, antinode is equal to what? So the formula now is going to change. It's going to be node is going to be equal to the antinode minus 1. Then the antinode is going to be the node plus 1. But when we're doing the normal, if the pipe is closed at both ends, it is opposite. Node is equal to antinode plus 1. Okay? So now in this case, meaning this one is going to be lambda to be equal to 3 over 2, or L is equal to 3 over 2 lambda. Now, let's go ahead and now derive the formulas for the fundamental frequency. So like we said earlier, if n is equal to 1, we're talking about the first overtone with the first fundamental frequency. If n is equal to 1, 2, 3, or 4, we're talking about 1, the first fundamental frequency, second, third, fourth. Okay? So now I can make lambda as a subject of formula. So the general formula will be the same. N divided by 2 times lambda. When n is equal to 1, we're talking about the first fundamental frequency. So I can make lambda as a subject of formula. So in this case, we'll still have 2L divided by n. So this formula will be the same as the one for normal standing wave. But the only thing is the antinode is going to be different now. It's the opposite of the node. What do I mean? If I've got 3 antinode, if I've got 2 antinode, I expect to have 1 node. If I've got 3 antinode, I expect to have 2 nodes. Okay? Now, what we have to understand now is this. Okay? The fundamental frequency will be the same thing. So remember we said V is equal to F. Now in this case I don't know the F I'm talking about, so I'll say Fn lambda n. Let's make Fn as a subject of formula. Fn will be equal to V divided by lambda n. We can replace lambda with this. So this will be equal to V divided by lambda n. Or lambda n, we are going to replace it with 2L divided by n, like that. The pipe is open at both ends. So we'll have Fn to be equal to V times n divided by 2L. So this will be NV divided by 2L, like that. So that is the formula now for any fundamental frequency. So if n is equal to 1, we'll have 1 times V is V divided by 2L. If n is equal to 2, we'll have 2 over 2V divided by 2L. If n is equal to 3, will have the same 3v divided by 2l. So I want you to see the trend which is happening there. V over 2l, V over 2l, V over 2l. Therefore, we can clearly see that this can be given as, I can isolate n to be here, then I say V divided by 2l. So V divided by 2l is the first fundamental frequency. So that's why we are going to see this formula now. So this formula is also important. We derive this formula when we're talking about the normal standing wave. So it's the same thing. So now, in this case, when the pipe is open at both ends, we are following the natural numbers. Okay, so you always have what we call the natural frequency. So you have, we follow the natural numbers. What do I mean? N is equal to the natural numbers. So we call it as natural frequency. You always have natural frequency because the pipe is open at both ends. So the only formulas which I want you to be familiar with are L is given by n divided by 2 times lambda. Then lambda n is given by 2L divided by n. Then the frequency n is given by this. Then also this can also be given by nf1. Sometimes they can give you the mass and the tension force of the string. Then you need to remember that V can also be given by the square root of the force divided by mu value. Remember we said mu is equal to the mass divided by the length. So then we can say the Fn can be given by n divided by 2L times V. Where there is V, let's put now the square root of F divided by mu. So this is also very important. Okay, now that is it when we're talking about a pipe opened at both ends. So the only difference with the normal standing wave is only the nodes and the antinode. So like we said, the normal standing wave, we are saying the node is equal to the antinode plus 1, but here the node is equal to the antinode minus 1, and the opposite is true. Now let's talk about the pipe open at just one end. So pipe open at one end. So if I've got a pipe and this pipe is open at just one end, so what does it mean? If this side is closed, then it comes as that. Okay. So one thing we have to remember is that this is the antinode, this is the node. Okay. Now since we know that this is just 1/4, so the length from there to there, the length is the same, it doesn't change. So what will be the length in terms of the lambda? So L will be equal to just 1/4. Okay. Now what if it is opened and then we have something like this? Okay, like that. So we know that this is 1/4 and this is half. So the length will be given by, so I'll say 1/4 plus 1/2. The common denominator is 4. So here I'll have 1, then here I'll have 2. So it will be 3/4. So I'll have 3/4 lambda. What if we have a different one? 1, 2, 3. So I'll have this. So this is 1/4, this is 1/2, this is 1/2. As long as it is open at one end, it's 1/4. Okay, it is 1 over 4. And then what we have to understand now is um, it's going to be 1 over 4 plus 1 over 2 plus 1 over 2, like that. So we are going to have the common denominator is 4. So 2, 4 there, I'm going to have 1 plus 2 into 2 is going to be 2, again plus 2. So I'll end up having 5 over 4. So now I'll say L is equal to 5 over 4 lambda. So I'm going to have L is equal to 5 over 4 lambda. So now what is going to happen now is I can clearly see that as we go on, the denominator will not change. Okay, the denominator will not change, but the only thing is going to change is the numerator. So we have got 1 at first, the second one is 3, then the third one is 5. So it's 1 3 4 1 3 5 7. So we can conclude that n should be, when the pipe is open at just one end, n can only be odd number. So if you know the odd numbers, then you know that n should be odd number. So in this case, we'll only be dealing with the what? The odd frequency. So n can only be 1 3 5 7. Yeah, then we keep on going like that. So now from here I'm going to have my general formula to be n divided by 2 times lambda, where n can only be the odd number. N is equal to 1 3 5 7, then we keep on going. So now in this case, we expect to have, when the pipe is open at just one end, then we expect to have the first fundamental frequency, the third fundamental frequency, the fifth fundamental frequency, and the seventh. You keep on going like that, the odd numbers only. So now let's go ahead and now derive the formulas. Okay, so if n is equal to 1, what will be the formula for frequency? The same. If n is equal to 1, so let's just write this: n over 4 times lambda n, meaning lambda n will be equal to, if I make lambda as a subject of formula, 4L divided by n, like that. So V is given by frequency n times lambda n. Let's make frequency as a subject of formula. Frequency n will be equal to V divided by lambda n. Where there is lambda, let's replace it by this. So Fn will be equal to V divided by 4L divided by n. That is the same as n times V divided by 4L. So this is the formula now for the fundamental frequency. So if n is equal to 1, if n is equal to 1, we'll have this. Then if n is equal to 2, we'll have 2V divided by 4L. If n, no, it can't be 2. Sorry. N can only be odd numbers. So if n is equal to 3, then you have 3V divided by 4L. Then if n is equal to 5, we'll have 5V divided by 4L. So you see that one thing here doesn't change. The only thing, this doesn't change. This part here, which I'm going to highlight in white, it doesn't change. So we can write the general formula to say F n will be equal to n times this, in the brackets, V divided by 4L. So V divided by 4L is the first fundamental frequency. So Fn can begin by n times this. This is also true. Where n can only be 1 3 5 7. You keep on going, the odd numbers. Now if you want to find the fifth fundamental frequency, you have the first fundamental frequency, so it will be just be like this. You plug in the values. So this is what you need to know when you're talking about the fundamental frequency. What if they ask you about the position of the node and the antinode? Okay, So if they ask you about the position of the node and the antinode, and then they are going to give you, let's assume to say n is equal to 3. So if n is equal to 3, meaning we have got 3 loops. Okay. If n is equal to 3, meaning we have got how many loops? We have got 3 loops. So let's see. In this case, if n is equal to 3, we know that n is the same as the antinode. Okay. So if n is equal to 3, then what should we know? We are going to say we'll have 1, 2, like that. So let's say it is open at just one end. Okay. So how many loops do we have? We have 2 here. Or let me just give an example of when n is equal to 2. N can't be equal to 2. N can only be equal to 3. Why are we saying? Because this is 1 over 4, this is half. So we said 1 over 4 plus half will end up having a 3 over 4. So in this case, n is equal to 3. So when n is equal to 3, when we're talking about the standing wave, when it is open at just one end, when n is equal to 3, meaning the orientation of the diagram will be like that. When n is equal to 5, then we'll have 1, 2, 3, like that. Okay, because this is 1 over 4, this is half, and this is half. So if we add, we end up having 5 over 4, meaning n is equal to 5. So when n is equal to 5, meaning we have got 3 loops in this case. Okay, so that is what you need to know. Now if they ask you to the position of the node, so you find that, you also find that, and that. Then the position of antinode, it will be that one, that one, that one. Now here is going to be 1 over 4 lambda. Then here you come there, yeah, you keep on going just like that. So this is what you need to know when it comes for the standing wave in air column. So let's try to solve some few questions. So the first question which I have is, a pipe is 2.46 meters long. Determine the frequencies of the first 3 harmonic if the pipe is open at both ends. Take the velocity as 343 meters per second at the speed of sound in air. Then part B, how many harmonic frequency of this pipe lies in the audible range from 20 Hz to 20,000 Hz. Then part C is saying, what are the 3 lowest possible frequency if the pipe is closed at one end and open at the other end? Okay. So now let's go ahead and gather our data. So from the information we have, so my length, I've been given that the length is 2.46 meters. What else? The velocity is 343 meters per second. And we want to find the frequency. We have been told that we need to find the first 3 harmonic if the pipe is open at both ends. If the pipe is open at both ends, so we're talking about 3 harmonic, meaning we're going to have this. I'll have 1, 2. So I'll have this. Like that. So it is open at both ends. So in this case, n is equal to 3. Because this is 1 over 4. This is 1 over 2. And this is 1 over. This is 1 over 4. So is it going to give you us 3? So 3 harmonic. So if I add 1 over 2, that is going to be 1 over 2. 1. No, it's not the 1. So we need to add another one. So this is how you know now. So if we're talking about they are open at both ends, and then we want to see, I'll have that point and that point. 1 over 2. So it is open at both ends, then 1 over 4. So n has to be equal to 3. So I'll have 1 over 2 plus 1 over 2 plus then 1 over 4 plus 1 over 4 is this. Yes, so this is now 3 over 2. This is when n is equal to 3. So when n is equal to 3, we want to find the fundamental frequency. Okay. So remember we said the fundamental frequency is given by NV divided by 2L. So we want to find the first fundamental frequency. The first three. So n is equal to 1. Then the velocity is 443. 2, the length is 2.46. So the first fundamental frequency will be 343 divided by open brackets 2 times 2.46. I'll get 69.7. 69.7 hertz. For the second one, if you want, you can keep using the same one. You just put 2 here. Then the third one, you put 3. Because when it is open at both ends, n can be any number as long as it's a natural number. But here I'm going to use this. So this will be now 2. The first one is 69.7. So the second fundamental frequency will be equal to 139. So you have 69.7 times 2. 139. 139.4. Then the third one, I need just to put 3 here. 69.7, like that. So it will be 3 times 69.7, 209 hertz. That is the third one. Now the next question is saying how many harmonic frequency of this pipe lies in the audible range from 20,000 hertz to 20 hertz to 20,000 hertz. So we want to find n. In short, they want us to find the value of n. So to find the value of n in this case, if we want this to be in the audible range, we have to say Fn will be equal to n times v divided by 2l. Our goal is to find the value of n. Let's make n as a subject of m. Now, which frequency are we going to use in this case? The frequency we are going to use is 20,000 hertz, because that is how audible it is. That is 20,000. The 20 is just the starting point, but where it is ending is at 20,000. That's why I'm going to use 20,000. So I'll say a 20,000 is equal to n, the velocity 343, to the L is 2.46. So if we cross multiply, we have n times 343. Then these two have 2 times 2.46, 4.92 times a 20,000. I'm getting 98,000. 98,400. Divide this by 343. 343. N will be equal to, I divide this by 343, 286. So 286.9, I can just say 287. So n has to be 287 for us to reach at the audible range. Okay. Then what are the 3 lowest possible frequency if the pipe is closed at one end? So if the pipe is closed at one end, remember the formulas we came up with. If the pipe is closed at one end, n can only be natural number 1, 3, 5. So these will be the first 3 lowest. Okay, so I'll say Fn will be equal to, we said Nv divided by 4L. So the first one will be 1 times 343 divided by 4, then here will be 2.46. The length will not change. So the first frequency will be 343 divided by 4, open brackets, 4 times 2.46, that is 34.86 hertz. That is the first one. Okay, that is the first one. Now we said that if you have the first one, then you can use the simple formula, which is the second one will be, there is this formula, Fn is equal to Nf1. So the second one will be the third one in this case. So it will be 3 times 3, 34.86. The third harmonic will be this times 3, which is 104. 104.75, so I can just say it is 104.57 hertz. So that will be the third one. Then to find this another one, which is going to be the fifth one, it's going to be 5 times the first one, which is 34.86. So it will be 5 times 34.86. That is 174.3 hertz. That is the third harmonic. The fifth, sorry. Now, that is it for this question. So two pipes of equal length are each open at one end. Each has a fundamental frequency of, each has got a fundamental frequency of 480 hertz at 300 Kelvin. In one pipe, the air temperature is increased to 305 Kelvin. If the two pipes are sounded together, what bit frequency results? So bit frequency is given by the absolute value of F2 minus F1. What does it mean? So you need to have two frequency. So I think I'm going to do a very good experiment the time we're going to have a class, so that I explain better under bits frequency. So if you have got two, let's say you have got two forks, okay, and then you want to you try, maybe just you get maybe a stick or maybe a wire, then you want to make a sound. So if you do both sides, pa pa, so you discover to say one fork, let's have this one. Let me explain here. If this is fork 1, then this is fork 2. So then if you are going to discover to say they are going to be different in the frequency, the way you are going to be hearing them. So if you produce sound here, again you also produce sound here, you are going to discover to say the sound for this one is going to be maybe blah, 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 blah. Then this one will be gong, 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 gong. So the difference in those two, that is what we call the beat frequency. So there are some situation where, but the best thing is we are going to have an experiment for this question, so that you understand better. So if I get to tie something here, then again I produce sound for this one, again for that one. So the difference, you are going to discover that this one, the sound will start now reducing, since I'm now tying something. So the sound for this one will be whoa, 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 whoa. Then the sound for this one will be like gong, 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 gong. So the difference in those two frequency is what we call the beat frequency. But the beat frequency, if it is negative, you just get the positive part. So it is the absolute value, the difference in two frequency, that is what we call the beat frequency. So in this case, I'm going to find two frequency. Okay, I'm going to find two frequency. Now I have got two pipes. These pipes, they've got the same frequency but different temperature. Okay, so meaning that so the first pipe, I'll have, this is going to be my first pipe. So they are saying it is closed at one end, so it is closed here, then it is open here. That is pipe 1. So we'll have another one here, it is also closed here at one end. So now one thing we have to understand here is that it is not open, we don't know where it is ending. So it is more like this is half. So if I get this and that one, I'll have one loop. Meaning that at this point here, in between, I'm going to have the length will be equal to 1 over 4. Because this is not going to give me half. Okay, it's not half. You can clearly see here. So you have this, you have that. Again, I'll have another one. So if I add this one and that one, that's when I'll get L to be equal to half. So in this case, L will be equal to 1 over 4. 1 over 4, it is in between half. Okay, so lambda. Even here, I'll have L is equal to 1 over 4 lambda. Now, the most important thing here is we need to find the length. Okay, because I have the frequency for the first part already, and I need to find the frequency for the second part. So the frequency for this one is the one which I've been given, 480 hertz. Now this 480 hertz, it is when the temperature was at 300 Kelvin. But we don't know the frequency when the temperature was at what? At 305 Kelvin. So the first thing we have first to find them, we want to find the frequency. So frequency, we start with the velocity. The velocity will be given by frequency times lambda. Okay. So I don't know from here. I know the velocity, because velocity I can find using 331 times the square root of the Kelvin is the 305 is the temperature divided by 273. So the velocity, I can know the velocity, which is 305 divided by 273, then the square root of this 1.056984445 times 331. So I'm getting 350. Okay. 305. Okay, so I'm getting 350 as my temperature, as my velocity, sorry, meters per second. Now that I have my velocity, I want to find the frequency. Let's divide both sides by lambda. So frequency will be equal to V over lambda. I know the V, but I don't know the lambda. Lambda can only be found if I get to know the what? The length. Okay, what do I mean? I have got L, is the length is the same. Okay, so if the length is the same, even the lambda will be the same. So how can we find the lambda? Initially, what we can do here, we can just do this. If I find the L, for me, since I have the frequency, I need also to find the lambda. In this case, what I'm trying to say is I want to find the lambda of the frequency of 480. But the first thing, I don't have the velocity, so I have frequency is equal to V over lambda. I have the frequency, I can have the velocity if I use now 300 Kelvin. So I'm going to have V to be equal to 331, the root of the temperature in Kelvin is 300 divided by 273. So V will be equal to 300 divided by 273. The square root of this 1.048284837. Then this times 331. So 347 meters per second. So the frequency, I have the frequency, I want to find the lambda. So the lambda will be equal to V divided by frequency. Okay, so what we're going to do now is the length is the same. So what I can do now, I can get rid of this. If the length is the same, then I can make length as a subject of formula in this case. Since if in case I don't want to make length as a subject of formula, I can just find the lambda, then I plug in here, I find the length, which is just the same. So lambda will be equal to, the V is 347 divided by the frequency is 480. So what will be my lambda? So in this case, my lambda will be equal to 347 divided by 480. 347 divided by 480, that is 0. I'm getting my lambda to be 0.723 meters. Now that I have my lambda, I can go ahead and find the length. So this frequency which we have, we will call it frequency 1. But even if you swap them, still you end up having the same answer. So the length will be given by half or 1/4 times this. I'm going to have, although it's the same thing, because I have the lambda. Now I can just plug in the values here. I say frequency is the velocity for the second one. We have found 350 here. Divide this by the lambda, 0.723. So what will be the frequency? So the frequency, which will be now the frequency 2, will be equal to 350 divided by 0.723, 483. Okay, so I'm getting 484 hertz. Is 484.01. I can just say 0.1, then hertz. Now that I have frequency 1 and frequency 2, if you want again, you can first find the length, but that is a long process. You can find the length and then you replace lambda with 4L, then 4 times the length, which is the same as just replacing with lambda. Now that I have got the frequency 1 and frequency 2, I can find the bit frequency. So the bit frequency is given by the F2, the absolute of F2 is 484.1 minus F1 is 480. So the bit frequency will be 484.1 minus 480. So we are saying 484.1 minus 480. So I'm getting 4.1 hertz. So that's the beat frequency. That was the difference in the frequency when you have two pipes, you plug them, so you have bo 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 bo, another one bo 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 bo. So the difference in those two frequency is 4.1 hertz. Okay,